Good morning, everybody. It's EMinar Wednesday, and today it gives me great pleasure to have Juan Carlos giving us a talk on multi-data, multi-scale probabilistic inversion. But before I introduce Juan Carlos, just very quickly tell you about who's coming up for the remainder of the season. We've got next week Alessandro Santillano on swarm intelligence applied to solving magnetotelluric inverse problems, so another probabilistic method. And then Phil Wanamaker on petrological systematics. That'll be wonderful, Phil, in 2 weeks' time. In 3 weeks, we have a couple of more Australians, Kate Selway and Sinan Azedin on their MATE code, on their MATE program, laboratory results code in MATE. And the penultimate EMinar is Yasuogawa, imaging fluids in the crust. And then finally, our last EMinar this season, I'm very pleased that we've attracted Lucy McGregor, who's the SEG Q1, Q2 distinguished lecturer, who'll talk to us about multiphysics. So today we have Juan Carlos Afonso, and I've known Juan Carlos since I think about 2008. And I was thinking during the early 2000s that the proper way to do geophysical modeling is actually to do it in a holistic way, and had all sorts of wacky ideas. And then I met Juan Carlos on a visit to Barcelona, and I found out he'd done it all. And so it's absolutely brilliant. What you're going to hear from Juan Carlos is, to me, the way forward, where we're looking at multi-data, multi-scale probabilistic inversion methods. So not only is the way we address the inverse problem, but the way we structure what we're going to invert. And so Juan Carlos's background is in theoretical computational geophysics, geodynamics. He integrates different disciplines such as mineral physics, potential field modeling, thermodynamics, nonlinear inversion, and physics of the mantle to enhance our understanding of lithospheres. There's a lot more to read, but I don't want to take too much time up. The one thing to say is that Juan Carlos is being applauded for his work, and he got the 2013 EGU Outstanding Young Scientist Award, the 2017 Anton Hales Medal of Australian Academy of Sciences, and the 2019 IUGG Early Career Scientist Award. So it gives me great pleasure to introduce Juan Carlos and ask him now to share his screen and come live and talk to us.
Hi, Alan, and hi, everyone. Thank you for the introduction, and it's my pleasure to be talking today, although it's very late in the night in Sydney. So apologies in advance if I get a little bit slow at some point. I will stop my video. I've been told that it's going to be better for the bandwidth. And let me share my screen, and hopefully you will be able to see the presentation. So can I confirm from anybody that you are seeing my presentation?
Yes, we are, Juan Carlos.
Can I get a confirmation? Excellent, fantastic. All right, so yeah, thank you again. You know, when Alan was sending the tweets and the reminders, I asked my wife, who's champion of Twitter, I said, hey, why don't you retweet this, you know, and give us some promotion. And she said, okay, yeah, let's do it. And then she retweeted the title, but she got a typo. And the typo, she wrote, instead of imaging the Earth interior, she wrote imagining the Earth interior. And actually, I liked it very much, because I think that's what we do most of the times. We're just trying to imagine things. So let's go on a tour of imagining what the Earth may look like. So before going on, I will obviously, I have to start, I always say, with the most important slide of the entire presentation. You know, the work that I'm going to be presenting and going to be showing to you is just not of, you know, my own work. It's the combination and the contribution from a lot of people. I've been blessed to work with fantastic people over the past 10, 12, 15 years. And these are just some of the key ones. But again, there are many more, and I wouldn't have a space on a single slide to put all of them. But let me start, and hopefully there is no a tremendous delay with the slides. But let me start with telling you a little bit about myself, because it's going to help you, I guess, in the context of the talk and what you're going to see in this presentation. I guess when people ask me, okay, what do you do? I usually I'm a modeler. That's the first thing I say. I like to model processes, physical and chemical processes relevant to planetary interiors. And my research usually is divided in two main streams, so I spend most of my time in these two areas. One is geophysical modeling and inversion, and the other one is perhaps what most people will classify as traditional geodynamic modeling, basically the numerical modeling of processes. And it's actually a very handy thing I've found over the years to be able to jump from one to the other, because it served me really, really well answering or trying to answer some of the questions that I've been interested in for many years now. Some of them well, you already know about it, but perhaps the most important one for today's talk is the constitution of the Earth's lithosphere, its physical and chemical state. It's bound, the lithosphere, particularly the continental lithospheric mantle, is bound to be a complicated beast, given the history that it has, the long history that it has. And although traditionally we were taught to think about the crust as this super heterogeneous mantle. I'm getting messages from my computer that my internet connection is unstable. So if at any point I cut for too long, just let me know so I can go back. Of course, when we look closer at the lithospheric mantle, we realize that it's actually more complicated than has been traditionally considered. And petrologists and mantle geochemists, of course, knew about this decades before geophysicists picked it up. And I was very lucky to spend a lot of time working with fantastic mantle petrologists and geochemists at Macquarie University for the past almost 12 years now. Now, understanding, of course, the thermophysical or the thermochemical structure of the continental lithosphere is not only of academic importance. If you are watching this seminar, you probably know this already, but there is a tremendous interest from the industry point of view, because it's accepted now that structures or variations, discontinuities in the thermochemical structure of the lithosphere correlates very well with the location of ore deposits and different types of energy resources. Now, I'm definitely preaching to the converter, I guess, here. But all I wanted to mention is when I started with this, I never thought that there would be so much interest, and it's getting more and more relevant given the present context that we found ourselves at. That I always say there's not going to be green revolution without critical metals. So the demand for understanding how to obtain these critical metals efficiently and with very low environmental impact is becoming critical. But we also realized very quickly that if we wanted to say something about the thermochemical structure of the mantle, working with only one type of data set was not going to be enough. So I guess there are, therefore, in my opinion, two different but intimately related problems here. One is the need for being able to image the thermochemical structure of the Earth in general. My interest, again, has been mostly on the lithosphere. So basically, how can I really use remote information, indirect information, to say something about the chemistry, the temperature, the pressure, the anisotropy that exist at depth? But related to that, intimately related to that, is also the need to understand the physical or the geological or the geodynamic processes that actually result in the signals or the geophysical signatures that we can recover or that we can study or identify using geophysical techniques. And that's why I told you at the beginning that jumping from one discipline to the other, numerical modeling or geodynamic model and geophysical imaging or geophysical inversion, has been very powerful connection or symbiosis in my own research. Now, for the modeling aspect, I spend quite a bit of time working on this. One of the things in particular that we've been developing is what we call multi-phase, multi-component reactive transport. And it's this idea that, of course, on the Earth, nothing is solid. You always have different phases, particularly at least two phases. That will be, your rocks and your melts, or your rocks and your fluids in general, and they are constantly reacting with each other, and they have different chemical components characterizing their physical and their chemical properties. So we work for many years on this, and hopefully, before I run out of time, I'm going to be able to show you some of these results and the connection that exists between this and what we're doing in geophysical imaging. In the meantime, I just wanted to highlight or point out 3 publications, relatively recent publications, that deal specifically with this second part, just in case I don't have time enough at the end to talk about this. But obviously the interest for today's talk, or where I'm going to be talking about the most, is about what we call the architecture of it. And for studying the architecture of the lithosphere, we use a technique that we call multi-observable thermochemical tomography, or MTT. And the premise of working the right thing, and we are using independent data sets in the right way, we should be able to come up with models of the Earth's interior that are compatible with each other. In other words, if your model is correct, you should be able to explain more than one data set. And of course, that for those who have been working with joint inversions, that's not always the case, and it's not always simple or easy to obtain. There are a lot of different pieces of information in this, or pieces in this puzzle, that need to come together in a consistent way to be able to obtain these more explicative models that can explain different data sets. And after thinking for a long time and working for a long time with this concept, we decided to work with a framework that we call the probabilistic, multi-observable, and internally consistent inverse framework. which is basically just borrowing from the statistical inference community or the Bayesian community, and combining these different data sets in order to obtain models of the physical state of the Earth's interior, rather than mapping a specific physical parameter. So, for example, traditionally we've been working a lot with specific data sets. In the slide, I hope you can see the slide. We have an example of, for example, using Rayleigh or Love dispersion data to obtain a velocity or a model of shear velocity of the subsurface. And for lack of a better name, I'm calling this a parametric tomography, just because, again, the interest is a physical parameter, in this case, the shear velocity. And traditionally, that's what we've been doing, and arguably we've been getting really good at it. But the multi-observable thermochemical tomography, what tries to do is, look, we do have more data available most of the times, and they actually have complementary sensitivities and complementary resolutions most of the time. And once you have all these things together, and you tie them up via a thermodynamic formalism, that is the piece that you need in order to connect the physical or the thermodynamic variables that control the physical state of the Earth interior with the geophysical signatures that we can record on the surface, you can bypass the step in the middle and go directly for the physical state, for the thermochemical state of the Earth interior. So basically what I'm saying is, here you take a lot of data sets with the complementary sensitivities and resolutions that you need, and go directly, or you invert directly for the main thermodynamic variables: chemical composition, temperature, and pressure of the Earth's interior. Once you have that, if you manage to do that, of course, the one in the middle, in between, like your classic tomography, is a free byproduct of your inversion, because you can always have it, but it's not the main point of your inversion. Now, I always say that although it sounds a little bit like magic, there is no magic here. And for those who are interested in the details that we cannot cover, of course, today, I can recommend at least these 3 publications. Each of them is like 30 pages each, and they are relatively heavy, but the details and the tests and the benchmarks are there. And again, as I always say, there's no magic here. It's just a lot of work and a lot of lines of code. But with this introduction to more or less the philosophy of multi-observable thermochemical tomography, I wanted to show you or take you through some examples that will illustrate what we can extract from this type of methodology. And at the risk of boring or disappointing some people in the audience, I like to start with the Western US, or Western Central US, because it's very close to my heart. It was the first time where we combine all these things, and it was the first real application demonstration. Eight data sets that are indicated there by with the red color, and in itself, as you can imagine, it is a big inversion. 8 data sets like this is just not trivial to do. But what you get out of it, of course, is a tremendous amount of information. And in this case, I'm just showing you some slices of, you get your VS, your shear wave structure. We actually got our VP structure as well, because we were inverting for P body waves. You get a full the full distribution of temperature, the full distribution of major oxides for the composition. Once you have your temperature, of course, you have a relatively good understanding of what the lithospheric structure looks like, which we're seeing here in figure A. We can predict regions of partial melting in the mantle and in the crust, and we can also have really good estimates of the crustal structure, particularly when you do this with gravity gradients, gravity anomalies, and receiver functions. It puts very tight constraints on the crustal structure. And a lot of really interesting things came out of this first application. And one of them, I guess, that to me was the most surprising one, and you can see in panel A, is that the cratonic part of the Colorado Plateau is almost inexistent. The cratonic root is almost gone. It's been eroded away. Another thing was the relatively thin lithosphere in the Rio Grande area, because previous receiver function studies have claimed that it was much deeper, and I'll come back to this at the end of the talk. And we could do other things, of course, like, as I mentioned before, you can get the full composition of your lithospheric mantle, and you can start comparing what you get out of the method, which basically uses only geophysical data, with direct observations about the chemical composition of the mantle, which you can extract from xenolith data. And in this particular case in US, I was rather disappointed in a way that what the model was predicting was very consistent with what xenoliths were showing to us in those regions where we had enough xenoliths of enough quality and well understood and studied. And it was disappointing because I'm always more interested in seeing the discrepancies. And I'll explain this a little bit better with the example in Africa later on, and you will understand why I was disappointed here. But in this case, again, it was just, okay, well, we're basically mapping what petrologists knew already from xenoliths. So nothing absolutely, or nothing really, really exciting here. But what was really exciting and opened up a new way of thinking about these inversions and open up solving new problems like the MT problem that I'll show you in a couple of minutes, was this idea that there was a very active sublithospheric mantle beneath this region. And people have been talking about the existence of small-scale convection, doing all sort of weird things and modifying or affecting the topography and affecting the chemistry and affecting the anisotropy of the mantle. And this is a really nice study in geology where that illustrates very clearly what it would be the classic approach to study this, which these authors did is they extracted a tomography, a seismic tomography result from data collected along this transect that passes through the Rio Grande Rift and the Colorado Plateau to the Basin and Range province. So they had this anomaly image, or image of seismic anomalies. And then what they decided to do is to try to guess what the lithospheric structure would look like. And they started running geodynamic simulations or numerical simulations of mantle convection in a trial and error way, changing parameters, changing geometries, until they got one that in their view would produce a synthetic anomaly map, which is the one that we have at the bottom, that will resemble the original one. And of course, here you have to have, I guess, a lot of imagination, but the main features were there, and they consider that evidence that yes, small-scale convection basically all the ingredients.
Sorry, Juan Carlos,
really,
we just lost
yes,
you for a minute.
I'm sorry. Yeah, thank you.
Just after small scale convection, could you just repeat what you were?
Sure.
Yeah.
Yeah. So they were interested in testing this idea of small-scale convection under the Colorado Plateau and explaining some of the seismic anomalies that existed there. So they used this approach where you run a number of simulations, tweaking parameters, tweaking the geometry, until you get something, a distribution of small-scale downwellings and upwellings that produce a synthetic anomaly, which is the one that we have at the bottom, that will resemble or that will look similar to what you have in the actual tomography image. And therefore you can claim that, well, you know, some of these features in the tomography correspond to downwellings, small-scale downwellings. So it is as interesting as it is. Of course, it's a little bit problematic and not very robust. So what we figure out is that we were getting out of these inversions pretty much everything we needed to really compute the Stokes flow in the sublithospheric mantle and see whether small-scale convection was really supported by the data, not by running simulations, but by using the geophysical data to tell us what the Stokes flow would be beneath this region. So we invented a way of doing this within the context of probabilistic inversions. And what you can see here is that there was indeed very strong evidence for small-scale convection cells occurring beneath this region. So for the first time, then we were able to map and image the flow and the actual circulation cells, not by geodynamic simulations, but purely by inversion of data. But we did it at the time in a relatively simplistic way. Actually, we use what is known as Stokeslet's approximation, and it's not very, very robust in terms of solving the real equations of mantle flow. So that got us thinking about better ways of doing this. And I remember when I think in 2013, when I gave my talk for the award that you mentioned, Alan, in the introduction at the EGU, at that time, I already presented this, and it was the origin of the idea of being able to do ultra-fast, we call them ultra-fast Stokes flow simulations that will basically allow us to have the Stokes flow in the sublithospheric mantle as part of the probabilistic inversion. And it took a long time, as usually, to well, it took a long time and a good PhD student, as usual, to sort out the details of this method. But I think it's last year or 2 years ago, by Olga Ortega was the PhD student that we supervised with Sergio Slodnik to basically be able to use Markov chain Monte Carlo inversion methods to solve the actual flow pattern in the mantle. And we use reduced basis methods in this approach. And let me spend 2 minutes with this, because it's very important and open up a lot of opportunities for us. There are many different ways of solving complicated problems, complex problems like 3D Stokes flow by what is known as reduced order techniques. In particular, we use one of these techniques, which is the reduced basis method. And the reduced basis method works in a very similar way to what you would do if you want to create a new color. In this case, we have like a light blue that we want to obtain, and we can obtain that by mixing different proportions of only 3 primary colors. So in the same way, when we want a solution, a particular solution for a very complicated problem, we can obtain that solution instead of solving the entire numerical problem if we have some basis which will be equivalent to our primary colors. We will have a collection of bases that we can combine in different proportions and obtain the solution to the problem that we're interested in. So, of course, there are a lot of details about this that you can get from the paper, but the principle is exactly this. So the idea is to have only a small number of bases that will be able to give a whole range of solutions for the problem of interest, instead of having to solve the problem, the full numerical problem every single time. In this case, it was the 3D Stokes flow problem. And the important thing of this is, I mean, reduced basis method has been very good in its own right for many applications, and it's a relatively mature method. But when we combine it with MCMC and the properties of MCMC, Markov-Chain and Monte Carlo inversions, it was a marriage in heaven. Because what happens is, the important thing is in the graph that you see here. If I were to solve an inverse problem that basically allows or requests or it needs the solution of a 3D Stokes flow problem, I would have to solve one full problem per iteration. And that is represented here by the dashed line. The dashed line is the one-to-one inversion step finite element solution of the 3D Stokes problem. Now, every time I iterate in my MC inversion, I need to solve a full problem. What happens with reduced basis? Well, what happens is, at the beginning of the simulation, I need to solve the full finite element problem, right? To create new solutions to new problems that the inversion is asking for. And as you can see, very quickly, I saturate the number of bases, and after certain amount of steps in the inversion, I almost don't have to solve any new problem anymore. Now, this means, of course, that instead of having a one-to-one, now I saturate the bases and I don't have to compute any new bases anymore. And what allows me really to do this, or to achieve this huge gain, is the nature of MCMC inversions itself, which is that it converges to a limited region of the space of parameters. So the closer I get to reducing the combination of possible parameters, the better it is for me to solve new problems using already computed solutions. So I don't need to, keep computing and computing. And it was an incredible realization that allowed us to solve again this complicated problem for the first time, and do fully probabilistic 3D inversions of Stokes flow in the mantle. But as we were doing that, of course, I started thinking, well, wait a minute, if I can do that, how about solving other complicated problems in 3D that have been traditionally very hard to do, or impossible to do actually, in a probabilistic way? And I remember conversations with Stefan Thiel and some with Alan Jones as well, that were very inspiring and really inspired me to say, look, I think we should do something about this. And we talked about it with Sergio many times. We decided to set up a PhD project. We were very lucky to get Coti on board, who was the perfect candidate for this project. And Coti has already addressed this in a previous seminar in this series. So I'm not going to spend much time here. But what this allows us to do again is to be, I think it's for the first time, full 3D, fully probabilistic inversions of magnetotelluric data. And not only that, the second part of this publication, which is at the moment under review, but you can get it in the archive, Earth archive, is where we present the joint inversion of MT and surface wave data for the large scale lithospheric structure of lithosphere. And again, very quickly, just to show you what is a synthetic, in this case, a synthetic inversion, but using realistic data that you have in the top panels, where you have the true model that we use to create the synthetic data. And after the inversion, this is, again, is a fully MCMC-driven probabilistic 3D inversion. You get at the bottom, the mean model recover and the maximum likelihood model. And as you can see, the recovery is very good, but this is just a snapshot, really a summary of the extremely rich amount of information that you get out of the inversion, because remember that you get full probability distributions over all your parameters of interest, or all model parameters. So you can study their correlations, their lack of correlations, their uncertainties. So it's a very rich and powerful solution to this problem. But of course, this is another story, and Coti already addressed this, I think, a month or 2 months ago. If you want more information, you can definitely download the paper. For the last part or the second last part of this talk, what I wanted to do is just to show you a few other examples, particularly the one in Africa. So let me skip this example in China, which is very, very nice, and I really like it. But let me go directly to the African continent, because it's one of the most recent ones, if not the most recent example that we work on, but it's also the largest, the biggest so far. So if you're seeing the slide, those red dots.
Sorry, we lost
indicates...
you, Juan Carlos. Just
yeah,
after.
Sorry.
Yeah, if you're seeing this slide, was the last we heard.
Fantastic. Okay, sorry. Yes.
And we are seeing the slide.
Now you're seeing, excellent. So if you're seeing this is the largest, the biggest model that we run so far. And on the figure, what you can see is the red dots, which indicates the resolution of the inversion. It was a really big inversion. It was a really nice collaboration with De Beers and academia. And what I'll show you very quickly now is what happens with the inversion. I have a movie that hopefully you will be able to see. And again, just let me know if you're not seeing what I'm describing. But at the bottom panel, you should be able to see the LAB structure, the MOHO structure, and then a series of observables that we extracted, because we inverted more than this. But the first one is the elevation, or absolute elevation. Then you have the free air anomaly, the geoid anomaly, the vertical component of the gravity gradient, and the phase velocities for 2 periods that we map for this movie. And what you see is that usually when you start, because this inversion starts from a preliminary 1D inversion, some fields are more or less okay, and some are horrible, like the potential fields, because of course these ones are fully 3D fields that you cannot capture really well with 1D inversions. But what you will see as I run the movie is that the inversion very quickly starts guiding your model towards a really good fit of all these observables in parallel. And again, we had more. For example, the Maruzzi tensor was inverted for the full diagonal, not only one component. Hopefully, again, you are able to see the movie, and by the end of the movie, you will see that all fields are already really well explained. And this is no joke, in the sense that again, for those who have worked in joint inversion, it's not that trivial to get a model with such an explicative power. So we're very happy with this model, and I'll try to summarize the main features of it now to you. In this slide, and hopefully again you are seeing it, or you will see it in a couple of seconds, I'm comparing the lithospheric structure that we obtained with 3 other studies that also estimated the thermal structure of the lithosphere, and therefore they estimated the lithospheric thickness. So of course the main features are there in most of these models. Perhaps the globic one is the one that departs the most, but the other ones, we all agree more or less okay on the first order. But when you start looking at the details, you realize Malawi rift, whereas
sorry,
on the other 2,
Juan Carlos, we lost you again. You said when you start looking at the details, you realize.
Yes, thank you, Alan. When you start looking at the details, you realize that things like the Malawi rift or the Lufulian arc in these regions that are very well picked in our model. Of course, they don't exist in the other ones, and that's it's a little bit puzzling. Why? Because of course, in particular, these 2 models have cratonic features on a present-day rift, which is strange. Another thing is that they don't really seem to pick the Lufulian arc, but and there are some other details in the Damara belt. It's perhaps not super exciting, this comparison, but when we go to the details, you will see that actually it makes a difference. So let me move on to another slide, because as I was telling you before, when you run some of these inversions, I always tell, particularly the postdocs or the students, when they come and they start working on this, I always tell them the same thing. Running the inversion in the end is, you can do it in a few months. But analyzing the results, the huge amount of information that comes out of it, it can take a few years. I have to go very quickly, and I have to cherry pick a few things to show you today. I would like to spend more time on this, but obviously I can't do it. But one thing that I wanted to share with you is the Congo craton was a big surprise, because it's one of the thickest cratons that we know, and we were all expecting, of course, that it will be a typical craton, but what we found is that it's not at all. This craton has been dissected somehow. Its compositional structure changed dramatically, and we were wondering how robust this was. We did a lot of tests, and it is a robust result. But not only that, we then later found out that the Bangui anomaly, which is one of the largest and most mysterious magnetic anomalies in the world, is located in this region and follows exactly the same structure as the one that we are seeing here. So there is something really interesting and strange going on there that we need to investigate more, and we are in the process of doing that. Another interesting thing is that your Cap Verde region, your Zimbabwe, the Tanzanian craton, they managed to retain a relatively depleted lithosphere, even though they were exposed to different types of geodynamic activity. But one thing that I wanted to show you today is when we discussed this with Steve Foley, for example, he said, hey, wait a minute. You don't have a lithospheric bridge between the Congo and the Tanzanian craton, which is what we always thought existed, because it's how we explain that the carbonatitic magmatism stops in the north of the Tanzanian craton, whereas you have a lot of magmatism on the sides, on both sides of the Tanzanian craton. But in your model, you don't have a bridge there. It's actually relatively thin lithosphere. So I'm like, okay, yeah, this is interesting. This is an issue here. Let's see, let's explore a little bit more. And what we found out actually is something very interesting, that on the sides of the Tanzanian craton, you can see that in the 3D images, you have an upwelling, basically hitting the craton and diverge in a way into both rift areas on the sides of the craton, which, by the way, the one that has the clearest upwelling and the thinnest lithosphere coincides exactly with the Nyiragongo volcano that erupted 2 weeks ago or so. And therefore, these regions are very rich in carbonatitic magmatism. Whereas when I go to the north, what we found out is that because of the large upwelling of the Afar region, you have two forced downwellings on both sides of it, as you would expect. Every time you send something up, something has to come down. And although you do have a relatively thin thermal boundary layer or lithosphere, the sublithospheric convection is sending mantle or sublithospheric mantle downwards, not upwards. And of course, you cannot have partial melting under those circumstances. So it was a very neat explanation as well of why you actually don't have magmatism. I'll show you two examples of when things work out really well with xenolith and when things don't really fit. So if you extract from the model in South Africa, the geotherm from the inversion, which I'm showing in panel C, and I compare it with a whole bunch of xenoliths from the group 1 kimberlitic group, which is around 90 million years old, both are very, very compatible. They are sampling what it looks to be more or less the same thermal structure. And okay, that's what usually geophysicists like to see and like to show, all these things are compatible, fantastic. But as I told you before, this is what happened in the Colorado area, and I wasn't really happy. They were excited about it. As it turns out, actually, the compositional structure that we obtain out of the inversion, which again is only geophysical data, when we look at it along a transect that's been analyzed by Alan Cobusan and co-authors a few years ago, we actually see exactly the same distribution that they describe using olivine crystals along that transit. You know, they go from a relative fertile domain towards the north to a very depleted domain towards the center of the Cap Val, and then back to a relatively fertile domain. And that's exactly what we see. Actually, it's almost too good to be true, because the numbers coincide almost too well when we analyze the results from the inversion. So the Cap Val seems to be very well characterized, and everything is nice and good. But then look what happens when you go to Angola. Now, Angola has a lot of kimberlites. Sometimes people talk generally about the Danto Kwanza kimberlites, but it's literally a whole bunch of clusters of different kimberlites that appear there. But there are a lot of samples and a lot of thermobarometry done in those xenoliths and xenocrysts. And what we saw immediately is that it's impossible to reconcile present-day structure with what xenoliths were sampling. And this is a more interesting result for me, because something obviously happened between the extrusion of the kimberlites and today. And if you look at the smaller Duluma cluster, which is a little bit south from the proper Danto Kwanza region, those xenoliths, unfortunately, and xenocrysts have not been dated, but there is evidence that they have been refertilized probably around 100, 120 million years ago. So they carry evidence that something happened in the mantle between the older kimberlites and what we can see today. And that is very clear. This is literally a place where you cannot, your xenoliths basically do not give you any information on the present day structure. So now I wanted to spend the last 10 minutes or so going back a little, which is the modeling of processes and how we combine that with geophysical inversion. So I mentioned multi-phase, multi-component reactive flow, something we've been working with PhD students and postdocs for a number of years now. And we managed to come up with a relatively nice way of modeling these complicated processes, not because they are complicated, but because once you add the thermodynamics, the chemistry, the mechanics, you can start tracking the compositions of these processes, not only the major elements, but you can do the same thing with trace elements as well, as long as you can, or as long as you model somehow the microstructure of your rocks, because trace elements are very sensitive to the mineral proportions that you have in your rock. So we managed to come up with ways of doing this, and I wanted to share very quickly with you just a little movie that hopefully will give you a better idea of what this does. And in this movie, what you will see is the simulation of an upwelling. So it's just a mantle upwelling that is hitting a thermal boundary layer or a lithosphere, and it's going to produce some melt. So particularly in the last panel right here that says melt, you can take a look at it and pay attention to what happens there. These are all the mineral phases that you have in your model. And when I run the simulation, what you will see is that the geotherm starts going up. Basically, you're advecting heat, and at some point at around 50 kilometers, you start producing melt. So I'll stop the movie right here, and as I said before, at 50 kilometers, you cross the solidus of the peridotite, you start creating melt. In this panel right here, what you can see are the characteristics of the mantle parcel. So basically, the blue lines are tracking mantle parcels, and on top of it, we're mapping the melt fraction as it occurs, and then the red lines that you see is the fluid. So the blue is the solid, the red is the fluid percolating through the solid, and as you can see, it's faster. Is more vertical, the characteristic, so it's a faster flow, and you start accumulating melt on the top, and you can see the same thing right here in this panel. It's exactly that. You start accumulating melt at the top. So if I keep running the simulation, what you will see is that a pyroxenite layer is coming underneath, and a pyroxenite has a lower solidus, so it's going to start melting at deeper levels than the peridotite, but it cannot really mix with the peridotite melt until both solidus are met. And when that happens, you will see that melt shoots up like crazy. Everything is mixed, all the melt is mixed. The features of the chemical therefore allows us to have.
Yeah, so we lost you again there. You just said
okay
about the features of the kink, I think.
Oh yes. So what I was saying is of course, the melt wants these different sources. Basically, the melt from these different sources mix together. The features or the chemical features of the melt that actually extrudes at the surface change dramatically as well. And we are able then to model these relatively complicated situations, in this case of mantle melting. And we can also track the composition and the physical properties of the residue. But remember that I told you before that we have micro models as well, because we can track the phases and the volumetric phases of these processes. So we can also model trace elements. Now, I'm not going to try to, again, I'm not going to spend time explaining too much about, this simulation, because I want to go and focus on the connection of this type of simulations with the actual inverse problem or geophysical inverse problem. So therefore, let me take you now back to the Colorado Plateau area, in particular in the Rio Grande Rift. As I mentioned before, when we were doing this study, there was various publications saying that the lithosphere here, or the base of the lithosphere, was around 120 kilometers deep, based on receiver functions. And of course, that was very, very incompatible, and it gave us a little bit of hard time when we came up with lithospheres of the order of 60 kilometers. So with these new methods of being able to model melting processes, and the Rio Grande Rift having a whole bunch of very recent basaltic melts being extruded, or that have been extruded in that region, we can take those samples and invert the compositions of the basalts for the actual process of melting. So that's exactly what we did. And the idea is very simple. If you have a thick lithosphere, you have an upwelling in the sublithospheric mantle, you're going to be able to melt up to the base of the lithosphere, more or less, but then you can't melt anymore, or at least you can't melt in the classic way of decompression melting anymore. Whereas in regions where your lithosphere is thin, you can melt more. So your degrees of melt and the composition, therefore, of the basalt that erupts are different if you melt a little bit than if you melt larger amounts. Your incompatible elements vary, or the composition of the incompatible elements vary quite a bit between these cases. So the idea is very simple. It's just this concept, but is to take these samples and invert their compositions for the actual melting process. And we were interested particularly, of course, in saying, okay, what is the base of the lithosphere that we need in order to produce these melts? So what I'm showing here are the data feeds. You have the spidergram of trace elements on the left, and the green dots are the actual data. And on top of that, or actually behind them, you have the distributions given by the inversion. And the same thing for majors. Now, this is a big thing, at least for geochemists, and the paper has been accepted in Geochemical Cosmochemical Acta, and because it's the first time that we do the inversion of both rare earth elements and major elements at the same time. But of course, it's very important if you have control on the majors, because they're very sensitive to the actual process. So we did this inversion. You obtain your results, and interestingly enough, if you look at the top, which is the marginals, or the joint marginals, or the joint distribution of the base of the lithosphere and potential temperature of the mantle, you will see that for the what I call set top is literally the base of the thermal boundary layer, the base of the lithosphere. So it gives you an answer of, look, 60 kilometers, which is really, really, obviously, really close to what we were getting, totally independent, using only geophysical information. Moreover, the potential temperature that we are getting, if you extrapolate it to a depth of 300 kilometers, for example, it turns out that is extremely close to what we were getting, again, totally independent from geophysical data, purely from geophysical data. Now, these two data sets are obviously totally independent. The methods and the inversions are totally independent, and they're both getting really, really similar predictions. That obviously took us, or made us think, that truly combine geochemistry or geochemical and geophysical joint inversions for characterizing the state of the lithosphere, particularly in regions with relatively recent volcanism, is possible. Not only possible, but is also complementary and attractive. So we started working on this, and with one of my PhD students, Sanchi-san, we're trying to apply it in China. The preliminary results are there and hopefully are going to be published soon, but we still have a few steps to go through in order to really be able to do this true joint inversion of geochemistry and geophysical data. So I will stop here and will give you with a summary slide that given the delay in the slides, I can't really do or play around with the animations of the slides, so I'm going to show everything at once. But the idea here is that geodynamic simulations, geochemistry or quantitative geochemistry, and geophysics, in the end, they talk the same language. They talk the language of the Earth. There are processes that impart their signatures to different data sets, but in the end, they ought to be related. And if we manage to understand a little bit better these processes and the connections between them, all of a sudden you close a big loop between simulations, quantitative geochemistry, and pure geophysics. And all of them inform each other, and all of them give you complementary information on the final question, which is how the Earth works. So I hope I managed to give you a little bit of a hint of how these things work and the potential that they have. And I will therefore thank you all and stop the presentation now, and I will open up for questions, of course. Thank you very much for your attention.
Well, absolutely brilliant, Juan Carlos. It's a pity about losing your voice every now and then, but I think we're able to interpolate across the gaps. Sometimes I called you in when the gap was too big. Yeah, wonderful.
Thanks.
Yeah, absolutely wonderful. I'd like to open it for questions. Could everybody please write the questions in the Q&A? And I'm going to, I'll read out the question so the question gets in the recording. And then the first one is a very interesting one from Yanuk, and excuse my pronunciation, Januka Atanaike. Excellent presentation, Juan. Inverting multiple data sets is no easy task by any stretch of imagination, let alone getting models to converge. I'm wondering if the inverted optimum lithospheric models in Africa are contaminated by sublithospheric structure, i.e., is sublithospheric sensitivity leaking into the lithosphere? This is certainly the case for seismic tomography inversions due to finite frequency effects.
I'm still on. Yeah. Okay. Fantastic. Obviously, fantastic question and totally expected. The resolution. I mean, there are a lot of things, of course, in this question. The leaking aspect. It can obviously always happen. Because in the end, the data that we use is a seismic tomography, is data basically that comes from seismic tomography. But there is one big difference here, and I really would like to point you to the paper of 2016 in US, and I would like to show you, if I can, a figure. If I can go back to my presentation, or actually my screen, to show you a figure that I hope I have. But before I find it, let me just try to answer. We've seen that if you take a model from seismic tomography, and which will be a typical thing to do, and convert the velocities to a thermal structure, or you use the velocities and specific thresholds of the velocities to define where your LAB will be. Something happens, which is particularly around downwellings in your sublithospheric mantle. If you do that, you tend to overestimate the thickness of your lithosphere tremendously compared to what you will get once you do the joint inversion, particularly with potential field data, because it's not the same, obviously, having 220 kilometers of lithosphere than having 100 kilometers. Is very hard if you want to explain the potential field data together with the seismic velocity structure. And what we see that happens is that the joint inversion tends to separate that much better, and we gain resolution for the sublithospheric part without having this huge leak of lithosphere into the sublithospheric mantle, or vice versa, because the different data sets that we have very different sensitivities to these processes. So we've done quantitative tests as well, particularly in Africa, and I have them, and I'm more than happy to show them to you. I think I can access them in overleaf. And we look at this in detail, and we are the features that we discuss and the features that we discuss in the paper. Of course, we are very confident that they're robust features. But yes, you always wonder whether there is some sort of contamination or leaking. And again, to be honest, we don't have a really final answer everywhere in the model. Some parts of the models are better than others. So yes, I mean, obviously we can't guarantee everything in the model, but the features that we discuss, we assess them carefully, and they are robust.
Yeah, I've got questions rolling in, which is great. I'm going to use my prerogative and ask a question about the Colorado Plateau is data rich. There's an awful lot of Rayleigh data.
Yeah.
But Africa is data poor.
Yeah.
And you're fitting actually there not Rayleigh wave observations as much as Rayleigh wave theoretical calculations from a pre-existing seismic model, right?
Yes and no, because we have done seismic tomography as well, combining ambient noise and earthquake tomography, and we've used a background as a background. We use the model of Andrew Schaefer, particularly for regions where basically there is no data. But then on top of that, we supplemented those models with real dispersion data from other individual arrays. And then on top of that, we did our own inversion for ambient noise and earthquake tomography. And I haven't shown that, but let me find it.
Yeah, I'm thinking particularly of that really intriguing gap that you showed in the Congo Craton. Now, the Congo Craton is particularly data poor, and so I'm just wondering if there was a mistake in Andrew Schaefer's model, would that mistake leak into your model?
I can tell you a couple of things here. That region is absolutely data poor, and we also wonder, what may be happening there. But we tried different combinations and different uncertainties of things in the Colorado Plateau, including dynamic topography and including errors in the tomography method. And that feature is something that it was always very, very prominent. So of course we did a lot of investigation then on that, and we actually found out that it coincides with very important structures, basically aborted rifts that happened in the Precambrian. And doing a little bit more digging into that, we found evidence of basaltic volcanism during that initial rifting. And moreover, some preliminary studies, particularly from the Mike Gurney's group, but even older than that, they analyze potential field and dynamic effects from convection simulations. And they basically say, we need something. They couldn't pinpoint exactly where, but they said, we need some anomalous density inside this craton to be able to make the, basically the data compatible. So we are not the only ones actually saying that, but we are the first who actually put a structure on it. Whether the structure is correct or not is another thing. But then you have the other thing, which is the Bangui anomaly, and that's why I really want to show you. The figures, because the Bangui anomaly is spot on. The structure, when you plot it on top of our compositional maps, they plot one on top of the other. And I talk about this with a group in Paris and MIT, specialists in magnetic modeling, and they were very interested in doing something about it, but at the same time they couldn't tell me exactly why or anything like that. But I think at this point, all these coincidences, yeah, they may be coincidences. I mean, you can never rule that out. But these structures are really prominent, and they are needed by the data. So my opinion is that there is something, and perhaps what Sue O'Reilly will say is that perhaps the most obvious thing is that, well, that's why you have the basin to begin with. And it's true, you have a massive basin there. Something must have happened to that lithospheric mantle to create that subsidence. And the argument of the dynamic topography, that's exactly what we tested. Our results are robust against dynamic topography effects. That feature still comes out of the inversion all the time.
Okay, well, perhaps while you're just getting to that, I'll quickly ask the next question, which is from Walid Ben Masur. Great talk, JC. How much did you pay for that? Great. What will be the next generation?
He's the guy who actually did most of the calculations for this one. So
what will be the next generation of the MTT, adding MTT plus REE? Can we apply the MTT for complex lithospheric architecture subduction zones?
Yeah, I know that you are interested in subduction zones, and you are not the only one. That we'll be able to do it probably next year, because I have a project now funded that it may require that. But at the moment, subduction zones are still a no at the moment. So we need to work a little bit more on that. And of course, the MTT plus REE is going to be very relevant there as well. So yeah, we have to wait a little bit for that.
Hendra Grandis asks, by reduced base for inversion, does it mean that we can obtain a complete interval of resistivity from, say, 1 to 1,000 ohms, or from only a part of it, say 1, 100, 1,000, for example? So basically, he's asking, by reduced basis, do you actually have discrete sampling of the spectrum, the parameter spectrum?
Yeah, not really. What reduced basis does is, imagine that you have your empty problem. So you need to solve the diffusive Maxwell's version, the diffusive version of Maxwell's equations to obtain your fields, and that involves a numerical solution, right? And we do it with finite elements. You could do it with any other things. So you solve that with all the degrees of freedom given to you by the discretization of your mesh. Now, imagine that you solve that for a particular structure, conductivity structure, right? And now you change the conductivity structure. So you change the conductivity structure, of course, your fields will look different, but your fields are continued, right? You have your apparent resistivity for as many periods as you want, and so on and so forth. You have the whole field. But of course, there are different solutions. And then you change your conductivity structure again, and you will have a different set of fields. So what reduced basis really does is it carefully and cleverly chooses these solutions, right? And combines them linearly. You can do it non-linearly as well, but effectively you combine, or you create a linear system that brings all these solutions together in different proportions, and they allow you to obtain a new solution to a new conductivity structure that is not contained in any of the other ones, or in any of the previous models. It's a new conductivity structure, but by combining previous solutions, which are your bases, you can create a new full solution for all your fields for that new conductivity structure. So that is what reduced basis effectively does. And you can think of it as a, I don't know, I thought about different examples over the years. You can use a wavelet expansion or a Fourier series expansion. The best thing is if you solve a finite element problem and you get a sinusoidal solution, will be the combination of basically the basis of all your elements, and that's it's a very high order solution. It's very general, but it's very high order. Now, if it is a sinusoid, if it is a sinusoidal solution, of course you can represent it with one term. You don't need the basis of all your elements. You can represent the solution with only one term, and that's what the reduced order modeling does, is the recognition that solutions to your problems don't really live in a space of tremendous amounts of degrees of freedom. They live in very small spaces. It's just that the degrees of freedom brought in by the finite element or the finite difference model is general. It allows you to come up with any solutions. But once you restrict your space of solutions by restricting your space of parameters, you can represent your solutions just with 2-3 terms. So that is the essence, the reduced basis. So it allows you to get new solutions based on a much smaller number of bases than the local basis from your finite elements. Hopefully I made sense and I answered the question, but if not, let me know, please.
Yeah, I guess if I could paraphrase, let's say you're deriving the current system for a 1 ohm meter, a 10 ohm meter, and 100 ohm meter bodies, and then when you combine them, you're going to take 30% of the 1 ohm meter solution and 20% of the 10 ohm meter. So you're not going to end up on a discrete set. You're still on a continuous set.
Yeah. It's literally a full solution to the full 3D problem. I mean, so I'm trying to find the figures.
Yeah, we're already an hour and 20 minutes, and we're beginning to lose the audience a bit, JC. I think.
Yeah.
I think perhaps we'll say thank you again to you.
No,
absolutely wonderful.
No problem. Yes, I'll stop sharing. Oops. Then.
And I'll just take back very quickly. Thank you again, JC, from everybody. And this recording will be up live as soon as Zoom tells me. And JC, please send me your PowerPoint so I can put that up. A very quick reminder that we have next week, exactly the same time, Alessandro Santillano talking about another probabilistic method, swarm intelligence applied to solve the magnetotelluric inverse problem. So at that, I'd like to say thank you to everybody to attending, and a very special thanks to Juan Carlos for this wonderful seminar. Bye, everybody. Stay safe and see you in a week.
Alan?
Yeah?
Can we stay on and hijack this meeting for CMTS, or shall we do another one?
I think we better end this meeting, Max.
Okay.
Yeah, bye. Bye.